Hi everyone, we will solve this worksheet 12. It's about planar graphs. So first question is about deciding if the given graph is planar or not. So here we're given in this part, we're given this graph, okay? So what do? We recreate actually this graph. But now we want the edges do not cross each other. So the remaining parts, the rest except this edge, the remaining part is the same. But as this edge and this edge cross each other, we need to rewrite this or redraw that as in this form. So you see, this is the planar form of this graph. And planar representation we say too. So what about this graph? And the part B it's given. So again we draw this again to edges do not cross each other. So here we had before this edge which crosses this and that's all, these two edges. So we draw it outside, okay, as in this form, and we draw this one again outside of this graph. So here we have, so this is a planar representation of the given graph. Now in the second question we're given again the graphs, and we will decide if there exists a representation, planar representation. So this one is homework for you. Let's do that B. So we're given this graph. So recall this corollary in the lecture notes. So it says if we have a graph which is connected and planar, simple, with E edges, okay, the number of the edges E, and the number of the vertices V, which is greater than 3, okay, and this graph, we assume also that no circuits of length 3, then it should satisfy this inequality. So let's check it for this given graph. We see it's simple, connected, and it has no circuits of length 3. And note that the number of the vertices of this given graph is 8, which is greater than 3, and the number of the edges is this 14. Now, if it is planar, then it should satisfy this. Okay, let's check it. Here we have 14 on the left of the inequality, and on the right we have 12. So we don't have the equality, it doesn't satisfy this inequality, which means the reverse of this corollary is correct. So this does not hold. If this does not hold, then either it's not connected or not planar or not simple, okay? Or it has a circuit of length 3. But we know all other assumptions that hold actually, then it means this graph is not planar. There is no representation, planar representation of this graph. Okay, let's look at the third question. So now we suppose we have a connected planar graph which has 8 vertices and each vertex has of degree 3. Okay. Now we will count the regions. Okay. Now recall this formula, Euler's formula, which says that if you have a graph which is connected simple planar with V vertices and E edges, these are the number of the vertices and edges, and R many regions, then these 3 variables should satisfy this equality. Let's check now, but to compute this, are, we need to first know E and V. Okay, we already know the number of the vertices, right? It's 8. Now it's enough to compute this number, which is the number of the edges. We know each vertex has of degree 3. Then it means we have 24 many connections. But we know between 2 points. So let's say we have these two vertices. So between these two vertices, we have one edge. But here we computed it 2 times, right? Because we said each of the vertices have degree 3. And we multiply 8 many vertices by this 3. So we computed each edge twice. So if we divide this one by 2, we will get the number of the edges. Here we have 12, which is the number of the edges. Now we use this formula to get the number of the regions. Here we have 6. Okay, this is homework. They are similar, so let's find 5. Now we will find chromatic number of the given graph. So look at the first one. Okay, chromatic number is the number of the colors, but the least number of the colors actually that you color the vertices of the graph, so that the adjacent vertices has the same color. So we start by this vertex A, okay? So we color it by red. Now B and F are connected with A, then the colors of these two vertices should be different from this color, which is red. So let's color them by blue. So here we have red, blue, and blue. Then, right, B and F not connected, so they can have the same color. But G is connected with, for example, B, so it cannot be blue. And it's also connected with red, so it cannot be red either. Then we need to color it by a different color. So let's say it's green, okay? Now we have red, blue, and green, right? Now look at C. It cannot be blue nor green, right? Because it's connected with G and B. But it can be red because it's not connected with A. So let's say red. And similarly, we can say E. We can color actually by red this vertex too. So what about D? It's connected with G, so it cannot be green, and it's connected with C and E. It cannot be red, so we can say about blue because it's not connected with B or F, so we can say blue. Thus, what's the chromatic number of this graph? It's 3 because we have 3 different colors. Okay. But we cannot color these vertices with that property with 2 color only, right? With 2 colors only, because we saw that A and G connected, so they should have different colors. But also A, B, and G connected, so all 3 vertices should have different colors. So we need to at least 3 colors to paint all vertices. Now look at this graph and start as usual by this vertex A and color it by red. Here we have the list. So we colored A, this vertex, by red. Now what do we have? We have a vertex which is connected to A, it's E. So we need to color it by a different color, let's say blue. And E and B are connected, so B cannot be blue, and it cannot be red either because it's connected with A. So let's say B is green, and C has a similar situation, so let's say C is green too because C is not connected with B, so we can easily color C as green. Here we have F, it's not connected with A. We can say it's red, and it's obvious that it's connected with E and B, so it cannot be blue and not green either. So we can say red though. So here we have red, blue, green, green, and red. Now we're at this situation, at this case. Now D is connected with B, so it cannot be green. As we see here, we have a green vertex too here, so it cannot be green. What about red? It cannot be red either because it's connected with A here, but it can be blue because it's not connected with E, so let's say blue. Now, what's the chromatic number? It's 3 again. We have these 3 different colors. Okay, so 6 is homework again. Let's find this. We're given an algorithm to color this graph, okay? So here are the steps, okay? We will first read the step and apply it. Now, the first step says that list the vertices of the given graph with respect to their degrees, okay? So we will order them with respect to their degrees, but in a decreasing way, okay? Now, the degree of A is actually 4 here, we noted, okay? We compute each of the degrees, each of the vertices, the degrees of each of the vertices. So what was the definition of the degree? It's the edges, the number of the edges, which comes from this vertex, okay, and goes to another vertex. So for that, for A, it's 4. For B, it's 4 too. What about E? It's 6. Here we have 6, right? So we computed them. Now what do? We will have a list such that first, so on the left, we will write the vertex which has the highest degree. So we see E has the highest degree, right? It's 6, so we write E. Then what do we have? Each vertex of degree 4 are the now candidates for the second vertex. What do? We just randomly order them. I chose this order, F, N, H, and I, okay? They all have the same degree, so you can pick any order you want. So I chose this one. Okay, then what do? We have these degrees now, and again I chose this order, so we have this list now. Now what do? We will start by the first vertex, so you can read this one. Okay, this is our process. So maybe you can stop the video and read this first. Now this is the process. We will first color the first vertex, okay? It says this. So let's say E to be red. Okay. Now it's connected with these vertices, right? It means by the process, we cannot color them by red. Okay. Now we see, but the other ones, the first vertex in this list, which has no connection with E, can be colored by red, which is F though, right? F is not in this list, it's not connected with E, and it's the first vertex in this list which is not connected with E, okay? A, B, and C are all connected with E, so we cannot color them by red, but F, okay? And we keep continue like this. We see H is connected with E, so we cannot color it by red. I has the same situation. And what about D? D is not connected with E, and it's not connected with F either, right? As you see here, it's not connected with F either. Because F is colored by red, we need to check that too. So D can be colored by red as it's not connected with F and not connected with E. Now, what about G? It's connected with E, so we cannot color it by red. And J has the same case with I actually, right? Or F, you can say. J is connected with F and I, so we cannot, sorry, I is not matter. I doesn't matter. So J is connected with F, so that's why we cannot color it by red. Now what do we do? Now we colored only these ones for now. Okay, we said red, and for F we said red, and for D we colored all these three vertices by red. Now what do we do? We pass to the second vertex, which has no color. For now it has no color. This is the answer actually. Okay. Now for now, ignore these ones. Now we will color by blue. A. First we chose this. Okay. Now what do we do? The first vertex after A, which has no color now, is B, but it is connected with A, so we ignore it. Now what about C? It's not connected with A, so we can color it by blue. And F is already colored, so let's pass to H. And H has a connection with A, so we ignore it too. What about I? It has no connection with A and has no connection with C either from this graph, okay? So we can color it too by blue, okay? And we ignore D because we already colored it. So what about G? We can color it because it has no connection with these vertices, okay? Now we have B, okay? We color it by green now, okay? We change the color. B has a connection, B has no connection with H, so we can color H by green, right? Here we don't see H. So H has no connection with B, so we colored it by green. And J has no connection with B and no connection with H, so we can color it by green. Now we colored all vertices by a color, okay? Now let's check on the graph, okay? Now we know J is green and H is green and B is green and E is red, D is red and F is red, right? So let's write them. B is red, green, green, green. Now blue ones. A is blue, and C is blue, A and C are blue, I is blue, and G is blue. So we colored all of them, and adjacent vertices has no same color, right? For example, A and B are connected and they have different colors. So you can easily check all of them, okay? It satisfies that property, okay? So the process is done and we colored all vertices with respect to that property, okay? So what's the chromatic number of this graph? It is 3, right? Which is the number of these colors, okay? So that was the last question. If you have any question, you can attend the office hour on Friday. Okay, see you there.